Hello everybody and welcome back to our Q&A session. Here we are having actually our studio, our Hyperspectral studio in the facility of Specim. I am Mathieu Marmion, working at Specim for about 9 years. I am a senior application specialist. We are going to speak today about the use of hyperspectral camera for recycling purpose. A month ago, we had a kind of similar session, which was more dedicated towards the food industry. So today we are going to speak, as I said, about recycling, many aspects about recycling. Here I am in Oulu. We have Harry, actually, which is controlling everything and making this happening. And we have also Jeff in New Jersey. So Jeff, if you can say a few words, please.
Yeah, thank you, Matthew. Thank you, everyone, for joining again. If you missed our first video, please make sure you watch that as well. We're going to be covering plastic sorting, as Matthew told you. I'm based here in New Jersey, so I'm in the United States. We are a global company. We're located all over the world. So I'll kick it back to Matthew, show you a little bit about the technology. I'll be back with the Q&A when he's done with his presentation, and we'll go from there. And hopefully we can answer a bunch of your questions. And if you have any questions whatsoever, please write them in the comment section, and we will answer them at the end.
Yes, it's important, actually, few words before starting. Since there is a delay between what's happening in the studio and what you are seeing, there is about 15 seconds. So it is quite important that you are actually writing your question. It cannot be really done in an interactive way of doing. So please write down your questions and we will answer to them afterwards. Also, if you want to download, we have a white paper which is about wasting no more. It's about recycling in general. So you can download it. Of course, you will have to subscribe for that. One thing, we are having now this YouTube channel, so we will be happy you to subscribe and also to like the video. That would be really awesome. But now, let's go back to what brings us here tonight, about recycling. Specim, we have developed some hyperspectral cameras, the FX10, FX17 and FX50. For recycling industry, the FX17 and the FX50 are the most relevant ones. They are just here. Just a brief history about Specim, maybe before to start. Specim has been founded in 1995 and we are now 70 employees. We are all mostly based in Oulu. In Oulu, we have our headquarters. We also have our CEO located in Helsinki. Jeff, as we were mentioning, is based in New Jersey, and we also have an office in Shanghai. We also have a network of distributors all around the world. This is how we are about our presence. We are making and designing hyperspectral cameras. An hyperspectral camera is basically a camera which records hundreds of bands. A traditional camera, for example, the one that I'm looking at now, or the one you are using for your holidays, records with only 3 bands, the red, the green, and the blue. With a hyperspectral camera, we record hundreds of bands. That means that we can have what we call spectral information. So when you take a hyperspectral image, for each pixels, you can have a continuous spectrum. And a spectrum, it is the way that the light is reflected, transmitted, or absorbed by a material. Every material, every plastics, they are different. They have some different chemical composition. And because their chemical composition is different, it is therefore possible to separate them because they will have a different spectrum. So for instance, you can see here, I have a computer, which is basically my laptop, with the software, which is processing the data in real time. And as you can see, there are different colors. There are some plastics which are classified in blue, some others in yellow, green, red. Those are classes of plastics. We have some PVC, some PP, some PS, different type of plastics. And there we actually have the samples. The samples, they are located on our scanner, on our 40 by 20 scanners. They are like this, just different type of corks, of plastics, and they are measured by the FX17 camera, which is just over there. We are making line scan device, so that means that they record spectra only over a line. And for each pixel of the line, it's possible to get a continuous spectrum. For the FX17, we are having 640 spatial pixels per line. For the FX50, we also have 640 spatial pixels per line. The FX17 is working between 900 and 1700 nanometers. This is what we call the near infrared. To give an idea, the visible spectral range, so what your eyes can see, is between 400 and roughly 700 nanometers. So now with the FX17, it's beyond this, and actually plastics, even if they all appear to be white or even with colors, you will highlight what is their chemical composition. With the FX50, that's the biggest one here, this one is between 2.7 and 5.3 micrometers. This one is called a MWIR hyperspectral camera for mid-wave infrared hyperspectral camera. This is a thermal camera. It means that actually it measures the spectrum the same way as the other one, the FX17, in a broader and spectral range for wavelengths, which is beyond, even beyond of that. Of course, the illumination is different. When we are talking about thermal infrared, we are talking about illumination in the thermal spectral range. To give you an idea, the illumination for the FX50, it is a road. It looks like electrical resistance, a bit like your electrical barbecue at about 650 Celsius, and then it emits wavelengths in the corresponding spectral range between 2.7 and 5.3 micrometers. These cameras, the FX50, will be very suitable to some black plastic, as I was saying, for instance, ABS, PS, PE, POM, and more. Just depending on your need, the FX50 most likely will be suitable. What can I say more about our technology? About the FX17, we have two types of interfaces. This time I am using the GIGI interface, but we also have the camera link possibilities. For the FX50, we are having only the GIGI interface. How a hyperspectral system is actually working, I already touched a few words about it. Here you have the camera, which is looking, as I was saying, through a line. Then you have the scanner, which could mimic actually a conveyor belt. Then the information is transmitted here to the computer. The computer then has a processing software. It could be real time, it could be offline, depending on your need. Then the software can compare the information brought by the camera to some spectral libraries that we have been inputting inside the system first. So if I go to give a bit more details here on the screen, I made a model, and you can see here for each plastics we are having PET, PVC, PE, PS, and PP. If we look at the spectra and we take the derivative, we can see some clear differences everywhere. And because of these differences, it is possible to classify. So if, for example, we have a sample and we don't know what it is, we just put it under, and then with statistical model, it will try to find what is the closest match, and then it will find out actually what is the relevant plastics. And then it's possible to have an actioner. For instance, if you have a conveyor belt, the output of the software could be actually an input to some valve, to some actioner to blow away some plastics which are on a free fall, for instance. Jeff, do you have some addition here?
Yeah, so I mean, it's a great introduction. That's basically the technology, right? It's a line scan device. We look at the chemical structure. So I think one thing that is often asked by potential customers and at trade shows is how this compares to machine learning or neural network. Um, so maybe Matthew, you can talk a little bit about that, how this is different from that, and how the training process works.
Yes, there are indeed like different type of algorithm. Here, in the processing that I am showing here, I'm using what we call a PLSDA algorithm, partially square discriminant analysis. So this is actually what we are here showing. But there are a lot of different type of modeling techniques. Artificial neural network, for example, you will have to have a teaching set of samples. It could be used as well for the deep learning. For deep learning, you need to have usually a larger set of samples. Those samples, of course, need to be samples that you know really well. So, for example, among the samples that I'm having here, those we bought them from the shop. So basically, we are certified. We know really well what they are. Well, this one is not written, but I know it's PET. So when you have those calibration set of sample, you can build your model. Well, first you have to measure them, of course. You can build your model. You can make your spectral library, and then that's how it goes. Another aspect which is important, it is also for the illumination for the NIR spectral range. With the FX17, you remember I was saying it was between 900 and 1700 nanometers. So that means here the typical illumination will be halogens. You remember that last time when we were having the Q&A session about the food industry, we were mentioning some other type of illumination, LEDs or supercontinuum laser, for example. Why? Because those white do not really produce heat. Here, with the recycling industry, heat is not as large the problem, but it will be actually something like not, how can I say, it will not melt your sample. I mean, like even if you have a little bit, it's not like when you are in the food industry with sewing. So here, halogen is still a suitable technology. I think this is really fine. I think I heard that we start to have already some questions.
Yep.
So, Jeff, do you want to take care of this one?
Sure. So, question: we have 112 waveband in the FX17. Question is, how can we relate these bands to the wavelengths 900 to 1700? So, I guess that means if you have 112 bands, how do you correlate that spectral resolution to the actual bandwidth of the camera, 900 to 1700?
So here, basically, we are talking about what we call spectral calibration. So the way we do at Specim, we take the camera and we make it look actually in front of an integration sphere, where inside we are putting some spectral lamp. When we are having some spectral lamp, we know really well where are the emission peaks. Then we build what we call the radiometric, the spectral calibration. That means that for each row of the detector, we actually allocate a band, a real band. So this is the way we are doing. Just maybe quickly how the cameras are working, because actually it comes out to me about asking this question. Here basically you are having the camera. You are having an entrance slit, so that's why you are looking only through a line. Then here you have a prism gratings, and behind you have a detector. So here you see the line. Each pixel of the line you have some hyperspectral or spectral information. Behind you have a 2D detector with a spatial axis here and a spectral axis here. And the way indeed, as I was saying, we are doing to make the spectral calibration, we use spectral lamp, and then with interpolation algorithm, we know actually for each row of the detector what is the corresponding spectral band.
Yeah, and I think you bring up a good point with the spatial and spectral resolution. I think it's important to keep in mind that the spatial resolution is dependent on the pixel size of the camera, obviously, but also your field of view. So we have different lenses that we offer to give you different field of views, depending on how wide your belt may be, how close the camera needs to be to the sample. All of that plays a role into what illumination you may use, what lenses you'll use, and we have lots of options for those. So it's important to always balance that spectral and spatial resolution concern. Next question is about a spectral range that we didn't talk about yet, which is into the shortwave infrared, going out to 2500. So do we have an extended spectral range that goes out to 2500? And we do. We have a SWIR camera that actually covers 1000 out to 2500 nanometers. Works the same way as the FX series camera, the push broom line scan device. But Matthew, if you want to talk a little bit more about the SWIR camera and maybe where it could be used for.
About the SWIR camera, as Jeff was explaining, is between 1000 and 2500 nanometers. So it is not an extended InGaAs, it is based on the MCT detector. The SWIR camera is also, as the FX50, fully temperature stabilized. We are having this kind of feature for those cameras because we start to be in the thermal world somehow, and it is important to keep the optics temperature stabilized so that the radiometric behavior of the camera is constant. So the SWIR camera, shortwave infrared, is temperature stabilized as well as the FX50. The SWIR camera includes 384 spatial pixels per line. It's a bit less than the other one, but this is how it is. What I can say about that one, as Jeff was explaining, we also have different type of lens for different type of field of view. Then about the question like, is it relevant to sort some other type of plastics? Well, based on what we know, with the FX17, about 90% of the plastic used commonly for house waste can be recycled with the FX17. This is true that for some others, an extended spectral range up to 2.5 would be relevant, but we are also having this product, so this is not a problem.
Great, yeah. Next question, what kind of pre-processing do you suggest? Now, I assume that depends on what you're looking at, but I guess in terms of plastics, or maybe what kind of pre-processing did you use, Matthew, for this example you're showing?
Well, here basically, well, first of all, there is normalization. Normalization, it is a step of pre-processing. What does it do? When you want to measure the reflectance of something, you need to know what is the incoming illumination. To do that, we measure what we call the white reference, and the white reference is acquired with a white reference style as it is actually here. This reflects the light perfectly well between 400 and 2500 nanometers. So basically I was putting this under the camera, and then you can measure the white reference, you can measure the incoming light. You don't have to do it all the time. As you can see, I don't have it anymore on the scanner. If your illumination is constant over the time, you don't have to do it really often. For the spectral range in the thermal infrared, this is not the same material. It is some blasted aluminum, but the idea is exactly the same. Then we measure what we call the dark reference. And in our camera, we are having some we are having some shutters, sorry. And those shutters actually avoid any light to enter the camera, and it's possible to measure somehow the noise of the camera. You don't need to do it all the time either. Once you have the white reference and the dark reference, you can do the normalization, and the normalization is basically the image you have minus the dark divided by the white minus the dark. So basically it's a ratio what is reflected compared to what is incoming, and you do that for all of the wavelengths. So this is the first step, the normalization. Then in this particular example, I was actually using the first derivative. There are a lot of pre-processing algorithms, but this time I was using the first derivative. The good thing with the first derivative is like, if you have a difference of intensity between two samples, but they are the same material, the derivative will kill somehow this offset, but it will highlight where you have some slope in the spectral, and where you will have some peak absorption or reflection peaks. So here I
Right.
was using this in order really to highlight where you have those. Depending on the algorithm you are using, some smoothing could be interesting to remove some noise in the data, Savitsky-Golay, kernel, running average, things like this. But in this particular case, it was only what I was doing. One thing I would like to add, we are talking about plastic recycling here, but our camera could be used also for different type of recycling. Could be used for paper, cardboard, construction material like concrete, wood, steel, and textile, of course. Any other question?
Yep. Next question. So how can we interface the output and classification with the processing unit? So sending it to another PC, and is there an API available?
Okay, so here basically the way we are working, speaking, we are making the sensor, the FX camera. The software you are seeing here, it is Perception Studio from the company Perception Park. This is not us. So the way we are working with some third-party company which are making software. So for example, there is Perception Park, which is making Perception Studio. There is also LuxFlux with the software LuxFlux. And there is also the company PerClass who is providing the software Mira. So here, those software are commercially available and are suitable for real-time data processing so that actually you can get a proper output from their software so you can have some actioner. Those companies, they develop their software so that it will match industrial requirement, so that it could be included into your ecosystem, your industrial ecosystem. Be aware that our camera can be provided also with a SDK, a software development kit. So if yourself, you will have the capability of getting the data directly from the camera, and you will have the capability in-house to make the hyperspectral processing and to make the machine vision system, you will be able to use our camera with the SDK. SDK could be C, C++, Python, some other people use it with different type of platform. It's up to you.
Yeah, I think that's important to note that there are these third-party commercially available softwares, but the SDK does come with all of our cameras. So you can, as Matthew described, you can use these other interfaces to kind of build your own program, your own classifications, and your own analysis. And that gives you a lot of flexibility. How do you overcome specular reflections? For example, if you have a thin layer of plastic, like a film, so something I guess that is really reflective. Since this is a reflective technique, the shiny, very reflective materials are difficult to deal with because you want to worry about saturation of your camera. If you're reflecting too much light, you can saturate your detector without actually getting any spectral information. So I don't know if you have any comments on that, Matthew.
Okay, so about specular reflection as well, I would like to have like a few words. Please look how our system look like here. We are having illumination which is double-sided here, and the camera is looking here. So basically the specular reflection will be a reflection that the camera is actually not seeing here. The camera will work really well here in this geometry is what we call diffuse. It will be diffuse diffuse reflection. For samples which are scuffed, not really shiny, this is really good. But we have noticed that when samples they are really shiny, for example, if you take around the TV, you know, the TVs, they have the edge which is really shiny, they are really black. And when our customers, they wanted to recycle part of that, there might be some issue because then if you have really shiny samples, then you will not have any diffuse reflection. So here actually the specular reflection is important, and we recommend actually to use the camera into a specular geometry. Imagine you will have your sample like this. The camera will be looking here and the illumination will be like this. So basically, you will see the image of the illumination through somehow or via the sample. And this actually, for the black plastic, we really recommend to use this type of geometry. Then the question was about thin film, which could be at the top layer of some of the plastics. I have to say that when you have multi-layers plastics, that can be very tricky to separate from each other. Sometimes the thin film, they can be measured with hyperspectral technology using constructive or destructive interference, but usually constructive. But yeah, when you have multi-layer plastics, that can be a problem.
Okay, yeah. Next question is about black plastics, which we touched on a bit, but I guess if you can show the FX50 behind you, the mid-wave infrared camera, can you say a few words on it? How good is it?
Yes.
And another question is how to deal with multi-layers. So I guess the first part first is the that's the FX50 you're holding there.
And actually, the multi-layer, I think I already answered. The multi-layer, it's a problem at the date of today, as far as I know. Some industrial partners, some people in university or making research, they may have an idea already about it, but me, I don't. But regarding the FX50 and the way it is working, this one, as I was explaining, is between 2.7 and 5.3 micrometers. And we have noticed that many plastic like PA, also PP, PS, PE, PC, they have some really nice features, spectral features between 3.2, let's say, and 3.6 micrometers. Then, if you go for longer wavelengths, around 3.9, PVC starts to have some interesting features. So there, actually, the FX50 can also solve them. And then there is a zone which is between around 4.2, 4.4 micrometers, which is not really usable because it is really sensitive to the CO2 that we are having in the atmosphere, or for example, when we are breathing. So here, basically, the CO2 will absorb everything. But then if you go beyond that, around 4.4, 4.5, it starts to have some interesting feature to sort, for instance, the ABS. And if you go even further than that, then the POM can be sorted. So here we have tested with different type of plastics, and we have noticed that this full spectral range, which is between 2.7 and 5.3, is very relevant for sorting black plastics. I was mentioning about the sample should be scuffed if it will be in the diffuse mode of the sorting, diffuse geometry. If they are not, if they are really shiny, it will be relevant to use specular reflection. At Specim, we are making also illumination for this spectral range, which is suitable. So here we can really help you in making your black plastic sorter.
Great, yeah, and I think it's important also to note the FX50, the mid-wave infrared. It doesn't have to be black,
yes.
Right, Matthew? It can be
yeah.
It can be plastics in general.
Yes, you are exactly. Yes, that's an important point actually, because the FX50 can do the black, but also the non-black. The FX17 can do the non-black, but not the black. And actually, the gray, it's a bit difficult. The FX50 can do all.
Yeah, it's an important to note. The next question is the FX17 suitable for classification of transparent polymers, especially thin layers? Often the conveyor belt of plastic weight sorters is black, which probably absorbs a lot of light. So kind of two parts there. So is it suitable for transparent polymers?
Well, that's the thing. If they are thick enough, so basically they will be so thick that they will have enough material to have some absorption feature, so then you will be able to see them. And remember, something which is transparent for the visible is not necessarily transparent for the NIR. That's one thing. But if it is really, really thin, if it will be like what you use like to wrap your food, for example, thin like that, those one, it will be really difficult.
Yeah, I think that's an important thing to note, is that transparent to the visible range, what to your eye, is definitely not going to be the same spectrally when you're out here in the near infrared or even into the short or mid-wave infrared. The other question I think is we can answer more generally. If the conveyor belt is black, then yeah, that's going to be absorbed, but you can classify your conveyor belt material, just like Matthew's probably done on the example that we're showing.
Actually,
with a black background.
Actually, I will show. If you go here to see the model, there is something called BG, which is a background. I asked to have it classified in black. And indeed, I decided to give a class to the background. So basically, if you would have a conveyor belt, and you have a conveyor belt, you should give a class to the material of your conveyor belt. Having said that, it is important that what you want to classify is different from your conveyor belt. That's something to really take into account.
We have another question on applying FX50 for black plastic sorting. So we've already touched on that. Next question. I assume heat from the midwave infrared could melt or destroy the plastic. Is there a recommended exposure time to avoid this?
Okay, our FX50, it is very sensitive. So typically, with our illumination, a typical integration time for our FX50, it's about 0.6 to 0.9 milliseconds. And this is for one frame. And remember, we are having line scan device, so basically your samples, they will be on a conveyor belt. So typically, our FX50 or FX17 camera will be used over actually a conveyor belt which is running between 1 and even to 3 meters per second. So if you think about it, the heat source of the illumination, it's about 650 Celsius. But if you have something, the sample is moving underneath at about, let's say 2, that's the middle, 2 meters per second, you will not actually heat up your samples. So if you will have a static belt, yes, well, okay, then it will melt. But think about it, in a typical operation, you will have a running conveyor belt and you will not have any issue. For instance, a few years ago, we made a system for paint monitoring based on our MVR spectral camera. And of course, we didn't want to burn the painting. That would be really, really an issue. So we actually checked at a speed of about, it was about 10 centimeters per second. The painted was heated up only by 7 degrees when it was moving under the illumination. So you can imagine that for recycling purpose, when it's moving 2 meters per second, there is absolutely no effect on your samples. You will not melt them.
Yep, that's good. Next question. How long is the expected life of a hyperspectral camera? It's always a difficult question for vendors to answer really about any equipment. We can talk here about our warranty, extended warranties, our service, but in general, that's a difficult question to answer. We see our cameras out there in the field 15, 20 years after we sold it. So that's always a difficult question to answer. I don't know, Matthew, if you have anything else to add, but we can talk about our warranty, which is 2 years on each of our cameras.
Yes, we have a warranty of 2 years with our camera. Keep in mind that in our cameras there is no moving part, only the shutter, but this is really a small thing. With the FX17, the lifetime is typically quite long. It's really long. Yeah, we start to sell it, I think 3-4 years ago. We have camera on the field which has been running a long time like this without any issue. For the FX50, we launched it last year. I must say that there is inside a Stirling cooler, so this has a lifetime, but it also depends how it is used. It depends on the ambient condition around the camera. We always recommend to actually have a casing around the camera which is temperature stabilized. So actually the Stirling pump doesn't have to pump too much actually, and then it extends the life of the camera. So yeah, this is what we can say.
Is this camera suitable to check the degradation state of polymers caused by UV light?
Well,
I
it
guess
depends. Yeah.
general that question is, you know, if the spectral signature changes, we can see that. But more specifically for degradation of UV light, I'm not sure. Matthew may have something to add.
Well, it depends. It's exactly as Jeff was explaining. If you have like a degradation which can be seen spectrally speaking, yes, it can. But if it is something like you cannot see, if it is only mechanical, for example, that no, we cannot follow it or monitor it.
Are you using any post-processing, for example, spatial information in the system that we're presenting, or are these plastics classified with pixel?
Okay, so here on what I am doing, no, there is not really post-processing. Or it depends what you call post and pre-processing here. If you mean, I see the question, for example, spatial information is a presented system or the plastic like, here it is only per pixels. But we know, for example, I think it is in Mira, I think they have some object recognitions. So if there is object recognition, then it will be possible, of course, to make an averaging of the spectrum over the average. But this is more like processing, something you can code by yourself, make by yourself. But I know that LoxFlux may have it as well, not only pixel per pixel, but you could also do it, to the best of my memory and knowledge, object-based.
Yeah, and to follow up on that, one question I get a lot is asking for a way to quantify how much of a material is present. You know, differentiating is one thing, being able to sort, but actually getting a measurement and a percentage of what's present is something I'm asked a lot. Can you speak to that at all?
Yes, here we can have two types of analysis. It depends if you are talking about mixture, plastic which are somehow mixture. It could be, for example, textiles. You know, textile you may have 50% of something, or you may have and 50% of something else, cotton, elastan, and things like this. So here, basically, you will have to build what we call a PLS model, which is a regression model. And the way it is done, you will need to have a certain amount of samples with different type of level of combination, and then you will be able to build your regression model, typically your PLS model. Then, based on this classification, you will be able to put a sample, and with interpolation, it will be able to give you an estimation of that. The second approach is more like when you don't have really quantitative analysis, but it's more qualitative. So, for example, you have a bag with some samples, and you want to know how many percent of that is PP, how many percent of that is PVC, and things like this. So basically, you will have to open your bag to make it seen by the camera as a whole, measured, classified, and then you can count how many pixels has been classified as PVC, how many has been classified as PE, for example, and making the ratio. So those are the two approaches depending on the situation.
Great. Yeah. Next question is, do you have any products that can be mounted on a drone? So we do. We recently launched the AFX series. So that has the FX10 visible near infrared, or the FX17, which is the near infrared 900 to 1700 nanometers in basically an all-in-one package that can then be mounted onto a drone. I don't believe we have any behind you, Matthew, to show.
Well,
but
I have to say, if you let me go like 20 meters that way, I know where I could find actually a mock-up of the AFX. So if I can escape here for like 10 seconds, then I can come back with a mock-up.
Sure. Sure. So yeah, we can show that. That would be really cool. So basically, what it is it has a GPS system inside with the computer and the FX camera that you see running behind Matthew. So that's all in one. It can be mounted to a drone, typically for agricultural study or things like that, where you want to fly a drone over a field for precision agriculture. Our other cameras can also be mounted on other drones or fixed wing type products. Matthew, do you have the model? There you go.
So basically here, it's an example of what can be mounted, for instance, on the DJI drone. Sorry, I was running, so I have to breathe. And basically inside, this is, for instance, the AFX-10. The AFX-17 will look the same. You will have an FX-10 or an FX-17 camera. So imagine you have that inside. And also, we are having a GNSS IMU unit which is embedded inside this. What does it do? Imagine you are flying on the drone, and sometimes the drone, you can use a gimbal, not a gimbal, but anyway, it is moving a little bit like this. So the IMU unit will actually record the position like this, the angular position of the camera. Also, the GPS, remember, you are flying over like this, will record for each flight line actually the position of the line. So the GNSS IMU unit will allow you to make georeferencing of your data. So I'm used to say actually that your flight line is somehow straight, but your georectified data is more like boogie-woogie in that respect. Then also, because hyperspectral data, they are quite heavy, so you can imagine it's like a lot of pixels with a lot of bands. They cannot be really transmitted from the camera toward a ground-based station. So the data, they have to be recorded in there. So actually this package includes also the computer, the embedded computer, so that the data can be saved here. The good thing with that is that it can be then remotely controlled from a ground station. You can tell the system, please start to acquire now and stop to do it. Or you can actually pre-plan where the drone is going to fly, and then you can make a pre-plan when the camera has to start the acquisition, when it has to stop, when it has to start again, and things like this. So that we can provide. The required payload for that one, the AFX-10 and AFX-17, it's about 2.5 kilos to the best of my memory. I think it's really close to that. And yes, we have that. So for the Matrix 600, it could be a possibility, for example. Yeah.
Yeah, and we also have a webinar dedicated to the AFX camera, so maybe we can put that in the comments as well, so we can link to that webinar if you want more information on just the AFX. Would you suggest a special kind of material for a conveyor belt? And I think we answered that in general.
Yes, we
want the conveyor belt to be made of something other than what you're trying to detect.
Yeah, exactly.
We have a next question. How high of a speed can we handle if we wanted to detect 3 millimeter square object? Well, we could talk about the frame rate of the camera, right? It's a line scan device. So when we talk frame rate, we are talking lines per second. And Matthew can speak a little to how fast the FX10 and the FX17 can go.
Okay, so for example, when you take the FX10, it's one. The FX10, if you want to measure all the bands between 400 and 1000 nanometers with a camera link interface, the full spectrum basically for all the bands will be 330 lines per second. With the FX17, if you want to measure the full spectrum between 900 and 1700 nanometers, it will be 670 lines per second. With the FX50, I have to quickly check the brochure. The maximum frame rate, it is 380 frames per second for the full spectral range. But think about it. Please look again to our application on the laptop. Here, in the model that I was building, you can see that the full spectrum is not really needed to separate all our plastics. For instance, if you look this region between the band 46 and the band 98, you can see already that all the plastic, they can be differentiated. And the good thing with our FX cameras is that you can select actually some region of interest, spectrally speaking. So if you don't want and you don't need actually to measure everything, you can select some bands where you actually want to put your focus on, and then it can speed up the camera. So if you select only few bands with the FX17, the camera can be at a much higher frame rate, something like 10 or even up to 15,000 lines per second. So here this is really something to consider as well. So to answer the question, yes, as Jeff was explaining, we are having like line scan device, but the question directly relates to how fast actually the line can go.
Yeah, and I think you touched on something really important there, Matthew, with the MRLI that we use, where you're able to select certain bands. If you have a spectral band that's smaller than the full spectral width, it does a couple things. Yeah, it speeds up the camera, the acquisition time. You can run your conveyor belt much faster, but it also frees up a lot of the data. You don't need all of the data to capture. So you can effectively use the FX10 or the FX17 almost as a multispectral camera if you don't need hyperspectral amounts of data. And that can be changed on the fly in the software. You don't have to change out filters or hardware. You don't have to touch the camera at all. You can do all of that in the software.
It could be done as well with the FX50. And one thing which is important as well, you have less data to process. So that means the processing time for the computer is much easier. So there is that to take into account as well. And one thing which is important, hyperspectral can become multispectral, but multispectral cannot become hyperspectral. So with hyperspectral camera, you can actually, you have much more flexibility than you will have with a multispectral sensor. And that's important as well, because if you have configured your machine for a certain type of plastics today, if tomorrow we are asking, can you add these plastics to be sorted in your machine, in your sorter, it can be added.
Yep, certainly adds versatility to your system. How would you describe the achievable accuracy? So, for example, if you classify a bottle cap, is all the area needed and every pixel of it classified correctly? So, yeah, this comes down to the spatial versus spectral resolution again. It depends how small of an area you really care about, how wide the belt is versus how small the materials are. We can use different lenses to give you different fields of views. We can crop the sensor to look at certain spectral regions to speed things up to get better spatial resolution in the plane of the conveyor belt. So there's lots of things to consider there. I'm not sure exactly what kind of resolution we're getting on this kind of system that we are showing behind Matthew. But we're clearly able to differentiate the different bottle caps in this setting. But if you have a wider belt, it may not be the case.
Yeah, well, it was possible here also because another thing that you have to take into account, the samples are clean. So if you will have dirty samples, the dirt or some label stuck at the top of something, this will have an effect on your classifier. It is important actually that your samples are as clean as possible. I know we are talking about recycled materials. Usually they are coming from the trash, so we cannot expect them to be as clean as if they would be new. But still, this is to take into account. And here it was a classification made pixel per pixel. It works really well. If you will make some object recognition, then you can make the averaging, and so on. So, but that's important to take that into account, yeah.
And okay, we have another question. How do different inks on labels and plastic sample influence the accuracy of the results?
Yes, actually, I will show you one thing. This sample, let's see how it is classified. Here, you can see it has actually some code bar, which is written, some barcode, sorry, which is written, and some text also, which is included. And this is also classified. I must say that some of the ink, sometimes they do not appear at all on the sample. I don't remember this one, but you can try. Here it is how the sample look like. You see, it was like from a yogurt pot. And I will put it like this to be classified. We can still see part of the drawings, but not everything anymore. So that means that sometimes the ink, by the way, it has a reflection in the visible, but not necessarily in the NIR. So some of them, they may have an effect on the classifier, some other, they may not. But again, when you make an object recognition, this is something that you should be able to detect and to separate from the rest. About the paper is more tricky. You cannot really see through. You will have it. It will be part of your image. Either you manage to clean it before, or it has to be a own class. So you know that when you classify paper as paper, maybe you know that here you have something to pay attention.
Okay, next question. Well, you're welcome. We answered one question already. So can you explain a bit more of how to do interpolation? For example, figure out the wave band 14 is exactly related to which wavelength?
So could you explain more how I can do interpolation myself, for example, to figure out?
So I think this comes down to the spectral calibration of the camera.
Yeah, it comes to that. Well, basically, if you buy a camera from us, you don't have to worry about that, because when we sell a camera, actually the spectral calibration is done at Specim. So if you will buy only a spectrograph, which is the optical part, by the way, we don't sell the spectrograph of the FX10, neither of the FX17, but we sell some other one. We also provide the system with a spectral calibration. So basically, it's what I was explaining. You need to put a spectral lamp. With a spectral lamp, you see where you see the line, the spectral line on your detector. You know that the dispersion is quite the same for the full spectral range. Usually you try to fit 2 a second or third degree polynomial curves, and then you will get your spectral calibration. But again, if you buy a camera from us, it will be already spectrally calibrated. So nothing to worry about that.
Is it possible to monitor the curing of a plastic? And that, again, probably comes down to, does the spectral property of the plastic change during the curing process? If it does, then absolutely that would be something you can monitor. I'm not sure if that is plastic dependent, but certainly something that could be possible if, assuming the spectral property of the plastic changes as it cures.
Well, I don't have anything to add. Yeah.
Oh, well, the next question is, so for example, a coating, monitoring if it's dry or not. So, we can certainly see the spectral change as it cures, as it dries, as long as there is one. You know, you can look at some of the heat contact. So if it's warm or if it's hot plastic, that will influence the intensity of the spectral curve, maybe not necessarily the actual shape of the spectrum. So that's something that you can certainly see. You can always see temperature change as a function of the spectrum, depending on how that changes as it cures.
One thing which is important here, we are touching another type of applications than recycling. And I would like to highlight that indeed hyperspectral imaging can be used for quality control or process control, for example, for the plastic industry. Indeed, if we know that over a process, plastics actually change, hyperspectral camera could be suitable to monitor these kind of things. But it needs to have a change.
Yeah, I think that's important to note, that you can monitor what plastics are there for sorting, but you can also do this as a quality assurance or QC check. If you're looking at plastic resin, for example, checking the bales that you're getting in, is it the percentage that you were expecting of that specific type of plastic or that material? And then as you process it and go out the back door, is it processed correctly? Is it still the plastic that you intend it to be? And what level of contamination may be there? I think another question that I get a lot is, what other applications in terms of the recycling industry can our cameras be used for? We're showing plastic here, but what other materials can we sort?
What type of material can we sort? You mean which type of different type of plastic is what you mean?
Different types of waste material, recycled material, not just plastic.
Oh, well, we can do like, well, basically everything which has a spectral signature. So it could be paper, cardboard, plastics. It could be, well, metals. It needs to be based on the color. What else? Textiles, construction materials. We have system for that. I mean, like that we sold for this type of applications. Yeah, that's what comes to my mind now. We know as well for PET flakes, we know that here there is also possibility to use our camera for that. Yeah, this is yeah, or rubbers.
Yep. So related to sensitivity, can small amounts of additives or contaminants be detected? Like additives, like plasticizers to fire retardants. So again, that depends on the spectral signature, one. So we have to identify the correct spectral signature that we can use to detect that material. The other side of that is the spatial resolution. How small is the contaminant relative to the size of your belt or the size of the other materials you're trying to differentiate it from? I think that all plays a role, and it's all important. So spatial, spectral resolution.
Yeah, just one thing, you were asking about fire retardants, typically the brominated ones. We have tried with our cameras. Few we were successful, but I would say a majority we were not able to detect flame retardants. Maybe because the spectral range we are looking at, they were not suitable, but still we were not able. We know that flame retardant may change the density of the plastics, so then related technology to measure density could be used for that.
How would you go about getting better spatial resolution? So for example, when trying to classify granular material, and again, that comes down to optics, same with any imaging platform, whether it's RGB or hyperspectral. When you're looking at spatial resolution, it all comes down to pixel size of the camera, field of view of the lens, collection efficiency, all of that plays a role. So as you get a wider field of view, obviously your spatial resolution per pixel is going to go going to go down.
Yes.
So if you wanted really good spatial resolution, you'd want a very narrow field of view lens and be very close to the material in order to pick up each pixel to have its own granular signal.
To give an idea, for example, with the FX17, the default lens is 38 degrees. So if you put the camera, which is at about 10 centimeters away from your target, you will have a field of view which is going to be about 7 centimeters. And because this camera will have 640 spatial pixels per line, you will have a pixel size which is going to be about 0.1 millimeter, which means about 100 micron. So here, this is what you will have. But then, if you have a high resolution, as Jeff was explaining, it is at the expense of the field of view, the general field of view you want to have. So then it's a trade-off. Field of view versus spatial resolution, or then we have a better solution. You buy multiple cameras and you put them next to each other. We will be really happy to go towards this kind of solution as well.
So 80% of common plastics are detectable in the 900 to 1700 nanometer range. So effectively, what percentage of plastics can be classified with the FX17, assuming they're not black, which you would then require the mid-wave infrared spectral region with the FX50. So sticking just to what can be detected with the FX17 here.
So what we have tested, we know that PET, PVC, PP, for PC, what else? PS, I think I said PE already. Those ones we know for sure they can be detected. Yeah, most of them they can be detected with the FX17, assuming they are not black. As I say, we haven't tried everything, but we know some of our customers, they really use the FX17 for sorting plastics and they are successful. So if it will not work, then it will not be successful.
So the next question came in 2 comments. So to detect multi-layered samples, is it better to analyze them top to bottom and have a separate class for the mixture, or is the resolution precise enough to detect multiple layers in a cross section? So this is being applied to a food container that's coated on the inside that has a different material than the outside. So again, this comes back to it's a reflective technique. You really have limited penetration depth with hyperspectral imaging. We're really just looking at the surface. Some material will have some penetration. You can see what's underneath. Or even what's through the label to whether there's food or something, messing up the actual seal of the plastic. And we've got an application put on that specifically. But being able to see through the label is possible. Having a reflection of what is on the surface of the label is also possible. So it really depends on the material, what's underneath. Certainly if you have a foil back on the label, you're not going to get through that aluminum foil, metal foil. You're only going to see the surface of that plastic.
One thing, in some application, it will be possible to use what we call transmission, but it is not that common actually for the recycling industry. Transmission will be that way: illumination here, sample here, and camera at the top. But this is not really common. And here it doesn't matter if it is top to bottom or whatever, because you go through anyway the full column somehow of the multi-layers. But again, multi-layers, they are really difficult.
Does the detection capability of the camera remain the same until the lamp goes out? I think that the best way to answer that is under identical conditions, the illumination, the conveyor speed, the frame rate of the camera, as long as all of that is remained constant, you shouldn't see any change in spectral intensity. But yeah, as depending on your light source, as that dims or as that changes over time, that would require a recalibration.
And the recalibration can be done very easily with a white reference, but we recommend you to change the bulbs.
Exactly. Do you also offer multispectral cameras for applications that require only a few bands? So no, we only make hyperspectral imaging cameras, but as we talked about with the MROI feature, you can turn a hyperspectral camera into a multispectral camera on the fly in the software. So multispectral cameras typically require filters or some kind of hardware change. That is not required with our camera. So as Matthew said before, you can't turn a multispectral into hyperspectral, but you can turn our hyperspectral camera into a multispectral. Yep, so here's the list of all different kinds of plastics. I know we've touched on a few of those that can be detected with the FX17. We are happy to do a test if you have some samples that you'd like to send. We'd love to take a look at those and see if we can differentiate all of them. We do feasibility studies like that. So yeah, if you've got some samples, you're not sure if we can differentiate them, great.
Hello to Turkey. This is our distributor, so we know. Is there any other question?
I don't see any other questions. We'll give you guys a minute.
Yeah, because actually we have been online for more than an hour now.
Yeah, so maybe we'll end there. Thank you, everyone that joined. Obviously, these are unusual times for us all. We are all mostly based at home and kind of thinking about your next project. If it includes hyperspectral imaging in some way, we're happy to reach out. We're happy to help and discuss your application specifically with you. We'll put up our contact information as well. You can find Matthew and I on LinkedIn. You can always reach out to us there. You can go to Spectrum, the website. Well, here's our contact information here. So there's my email address, Matthew's, and then the general info email address. But if you're in the United States or North America, Canada, you can contact me directly. If you're outside of the U.S., around the world, feel free to contact Matthew or that info general email box, and you'll get someone from Spectrum to reach out right away.
Okay, thank you as well on my behalf. And please don't forget, subscribe to our channel. You may also like our videos. I hope it was interesting for you. This time we kept the technical part shorter than last time so that we had more time to answer your questions. So if you feel that the technical part was a bit too short, please do not hesitate to go back to actually the first Q&A session we held about a month ago. So thanks for attending, and as Jeff was explaining, if you have any question, please ask and stay safe. Bye-bye.
Bye, everyone. Thank you.